trending here, and I want to try to actually map that to maybe a physical process that generated it, or use that to say, what would explain this in the actual underlying understanding. So this now is getting a little bit more, it's not, this isn't kind of the space of easy problems anymore. This actually requires a lot of work once you've done it, but it can be really useful for getting an idea of kind of underlying structures that exist. And they're, the simple techniques like PCA, you just get what you get. But once you get into the neural network-based techniques, you start to be able to actually lean on the clustering or lean on the embedding to highlight certain things that you're interested in. And you can start to ask specific questions with it. So I want to try to move in that direction. And then there's a code example which I'll walk through that uses Keras. So hopefully it will be pretty similar to what we just did, or at least similar enough that it's not really confusing. But there are filters. Okay, so one big motivation for this that happens in industry is if you could just get away without having to have labels, then you could get a lot more data than if you actually have to have someone go and do a human decided label. You might even have things where you don't even have the ability to say what the label should be. You think that there's structure there, you think it's important to get the structure, but who knows, is this actually happy, or is this actually positive something? I guess people actually study that in a lot of detail to try to standardize what it would mean for this to have this kind of valence or that kind of valence. And it might be nice to know if that structure is actually a real structure of the data, or is that something humans impose after the fact. With language, of course, humans impose it either way. So that kind of thing gets more towards, I think, the scientific applications of this. But you can also use this sort of thing for pre-training. If you find yourself in a need to have a lot of unsupervised, a lot of untrained data, it would be useful to leverage to get your model to actually work. Okay, so the basic idea of embedding is you've got some kind of very high dimensional thing you start with. Your data has, whether it was 3,000 features in the satellite images, or it could have 300,000 features or 3 million features. And you really want this to be in a low dimensional space so that you can actually visualize it by eye or do manipulations of it. And when I say low dimensional, for visualization, of course, that's usually 2 or 3. But in the kind of space of where people use embeddings, 256 dimensions can be considered low dimensional. Because you can actually work with 256 dimensions in a way that with 3 million dimensions, you just can't do it. Even if that seems like really oddly abstract. So PCA basically looks at the data and finds the directions of variation and tries to find the axes such that those variations are independent from each other, at least linearly. And then you can just take the biggest components. I'm going to go through this very quickly since we're going to be good about it. The thing about PCA is it's linear. So if I have data that has some kind of nonlinear trend to it, I may find that the PCA axes don't tell me much at all. They don't actually capture the structure of the data, and so they're not getting me anything. If I have some kind of nonlinear way of working through this, I could, for instance, run a spline through the data and then have the variation perpendicular to the spline, something like that. I can draw that. But we would like to have some way of actually getting that kind of structure to be learned. And with a neural network or some other arbitrary nonlinear model, as long as you can find what that spline and perpendicular is supposed to be doing for you, you can just optimize the loss of that model and then get something that tries to organize the data in such a way. So auto-encoders are one way that people do this. And the idea there is that you've got your input and you impose some intermediate representation that's very low. So this task basically is given X, I'd like to predict X. And that's trivial, but it's not trivial if I'm forcing it to do so via this proxy Z, which is very, very small. If my X is 1 million dimensions and my Z is 2 dimensions, every point in that 2-dimensional space has to tell me exactly what 1-dimensional X I have. And assuming that I don't allow this thing to just be infinitely dense, but actually put some noise and kind of constrain it, then it's going to try to find the things that are the most informative about the overall structure of X first and prioritize them. Because that way, let's say 1 dimension in Z, if I can predict 1,000 dimensions of X with 1 dimension, if I encode it one way, or if I encode it another way, I just get 1-to-1, the model is going to do better if it can actually explain more of the dimensions of X with fewer dimensions of Z. So it's kind of like a compression algorithm. I want to zip this data down, and then I learn that compression algorithm, and the structure that I get tells me something about the structure of the data. So the characteristic of autoencoders is it's kind of invertible, right? I have to map from X to Z, but I also have to map from Z to X. And that constraint can be pretty severe. There can be things where even if you make Z quite large, it's just extremely hard to learn this mapping because learning that function inverse is very complicated. There's this thing that like autoencoders on images, even if Z is quite big, are often very blurry. They have difficulty reconstructing even as much freedom as you want. So there's another class of things which is these kind of non-invertible things like TSNE that you've heard about, and UMAP is another one. It's kind of a similar family. The reason why you might want to use UMAP instead of TSNE is that with TSNE, if you add one new data point, you have to rerun the entire thing. So all of your embeddings can move around. But with UMAP, you actually learn a function, and you can put your data into the same space as the old data. So it has that kind of property like PCA does, where you can actually use it to define structure and then see how it relates with new observations. And that can make it a bit more convenient for pre-processing for other machine learning that you will do later on. Because you don't want to just use it on the data you have. You want to use it on some data you don't have yet. And there are Python packages that are as well that are pretty simple, but I'm not going to go into it. Okay, so back to autoencoders, another problem, and this has to do with this kind of blurriness, but there's a general sense. I'm still using this X space to define what's a good reconstruction, what's a bad reconstruction. And if I were doing this on something like images, I might find that, I have these two images here that look very, very similar to each other. But actually, I've offset this one by, I think, 3 pixels in the x-axis. And so when I take the difference, it says, actually, these are almost 50% different from each other. It's almost chance level reconstruction, if I just assume that they're the same. But probably if I want to find structure that's meaningful, sometimes I might have things like this that I want to be considered the same, but are really different in the detailed representations. So that sense of similarity, I need a way to inform the model what does similarity mean in this space, so that I can actually pull out structure that matters and not arbitrary structure like I can translate an image by X or Y or rotate it or scale it and get a latent space that just has all the translations, rotations, and scalings with nothing else. So this leads into something, a general class of things which is similarity-based embeddings. And the idea here is it's not fully unsupervised. You come into this with some sense about whether points in your data are more or less similar to each other, but only that. You don't know exactly how you would compute where to represent the data, but you have some reason to believe in the similarity or difference of the data. So an example for that might be if you're taking time series data, think events that happen closer together in time, you might have a prior expectation they should be more similar than events that happen further away in time. Or if you have satellite images taken of places that are very close to each other, you might say, let's see, I'm going to just say that these should be more similar than points that are very far away. And so then what you want to do is optimize this embedding function so that things that you say are more similar are closer to each other than pairs that you say are more different. And that leads to this specific algorithm, which is this triplet embedding. So the idea here, it's a triplet embedding because you have triplets of data points that you consider. And you pick 2 of them intentionally to make 2 that are in the similar family and 1 that is dissimilar to both of the first 2. If you embed each of them into the space, you get 3 coordinates, 1 for each point, which are the Z's. And then you can get distances. And you can define that distance however you want. You can use Euclidean distance, you can use a dot product or cosine distance, or something really fancy if you want. It kind of, it can impose different kinds of structure, but more or less it doesn't matter. And then all you want to do is compare the distance between the similar points to the distance between the dissimilar points. And you want the similar points to be closer than the dissimilar points. So if I write that in the form of a loss function, and that E is the expectation of that difference over the data set, so that means essentially the average of the difference between dissimilar minus similar distances, I can get a loss function. Now, if I just do that, the points will just run, a few points will run out to infinity, so they drive all of the distances to other ones to be very, very large, and then sort of in that very large scale, they can hide the actual structure that you're trying to capture. So what people do in practice is they use this hinge loss. And this essentially says, okay, I want the dissimilar points to be further away than the similar ones, but I don't really care if they're really far away or just far away. If they're greater than a certain distance, it's all the same to me. So I just want them to be disconnected or connected instead of actually being specifically ordered by the distance. And that gives the embedding a lot more flexibility to encode structure without having things get pulled by very far away points. So this triplet loss here, I just take the differences, I add an offset, and then if 0 if this thing is negative, then I have 0. And if it's positive, I have that thing. Right? So this basically, the code example that I want to walk through implements a network that optimizes this loss with the same kind of convolutional neural network architecture that you use for the sublet data. And that's kind of the idea, that you can take that entire backbone of that network, but instead of outputting a classification, you output this, which I had on the slide, you output these Z's. Right? So you map the image instead of to 6 numbers that have to add 1, you map it to 2 numbers that have no constraints. But it's just an output, right? Everything else about the neural network can be exactly the same. Okay. Yeah, so here's the actual, here's what I just said. You start with the standard architecture, and then instead of having a softmax output or a single output, you just make it linear. And you choose the size of that output to be whatever the embedding dimension you want, 2 or 3 if you want to visualize it. Then you create these batches made of sets of 3 images, 2 similar and 1 different. You get this triplet loss and backpropagated triplet. Okay. So if I have this, what can I actually do with it? And this is a little bit tricky. If you're using something like TSE and you see a bunch of clusters, it doesn't mean that there's necessarily really clusters there. And that's kind of, you can see that kind of thing happening a lot in embedding. They'll have some bias that they impose on the structures that emerge, and you have to learn to kind of read that embedding. At the same time, it's really hard to say, like, because I have a peanut-shaped cluster, it means this scientifically. So this is really a guide. But there are some things that you can do. One of them is if you have some kind of label data, you can plot the label data against the embedding and see if it's actually captured whatever underlies that label data. So here, this is TSNE on raw pixels. It doesn't know that a 1 should be similar to another 1. It's just looking at what things are similar to each other, what sets of things are similar to each other. But if I plot it with respect to labels, all of the different digits get very cleanly separated. So I know I'm repeating the previous talk, but this can kind of give you a bit of confidence that the embedding is picking up something real rather than just creating some arbitrary structure out of nothing. And if you have these other things, even if you don't necessarily, these aren't necessarily the things that you really want to classify, it can help you interpret what that embedding space is actually telling. Then once you have this, you can actually start to do things like measure correlations between the embedding coordinates. Yeah.
Do you know what this image would look like if you just use the difference between 2 points instead of the triplet embedding?
This one is TSME.
Okay.
So it is using some kind of distance between the points, but it's like it's Euclidean distance, and then there's a statistical test to say whether points should be near each other.
Because I think I missed, or I didn't understand why you said it could run off to infinity, and I think I didn't get that part.
So for the triplet embedding, so think about the balance between the similar and dissimilar points, right? If I have 1 point here and I have 1 point there, what is my loss going to be dominated by? Well, most of these points, if let's say this class has 3 points that are similar and the rest are dissimilar, then this sorry, I think I need to do it like this. If I want to make, I need like, let's say 3 of them are here and 1 of them is here. So in this case, the things that I want to make small are these and this and that. And then the things I want to make large are all of these other ones. So the problem is these are not balanced. I might have the positioning of this cluster be dominated by the fact that it wants to get away from the fact that there are more dissimilar points in the data set to it than there are similar points that are easy or hard to separate. And so once it's found a dimension like this where it actually can have most of the cluster go, rather than like rearrange things to be more efficient, we can just make this cluster keep getting further away.
Oh,
And
yeah,
it'll also
okay,
keep
yeah.
going down forever.
Yeah, okay.
But with the hinge loss, it will stop gaining a benefit for pushing this thing really far away.
Okay. Thank you.
Yeah, so the other thing about this kind of embedding is if you have a sense of similarity and you know that certain things should be front part or not, but it fails to capture that. And this is maybe in the satellite image, this would be a good example. So let's say I say my similarity sense is geographic nearness. Points that are close to each other in latitude and longitude should be clustered close to each other in triplet embedding, and faraway points should be far away. But I've got a forest in Brazil and I've got a forest in Japan. And my view of it isn't enough to actually tell the difference between the kind of forests that Brazil has and the kind of forests that Japan has. So I might find that even though these points should be very far away, those clusters are actually kind of fused. And they have some kind of neck or overlap point where that loss is developing a lot of tension. That can tell me that the kind of input I use, which might be pixel values at a certain resolution of satellite image, is not necessarily able to separate all examples of this, but that there is some kind of recurring pattern that shows up in different regions of the space that I'm operating in. So if I were to learn a triplet embedding like this, I might find that the different points in the space actually correspond to different kinds of terrain rather than different geographic locations. And that's actually the example I'm going to show. So it's a bit hard to interpret, right? I wouldn't really be comfortable writing a paper saying, oh, the triplet embedding collapsed the points and therefore deserts exist. But it's kind of useful, I think, to understand the data so you know maybe what you can say about it or what you can investigate. Okay, so if you go to Colab and you open up from the GitHub this triplet network Keras IPMB. So there's, I know at the end, the last time I said that you had to get this data and put it on your Google Drive so that you could work with it. Have people done that or not? Yeah.
Probably not.
No.
Probably not.
I think the URL is in the Google document. I already put it there. So there's a directory with a bunch of satellite images pulled from Google. And you basically need to have that directory exist in your Google Drive with the same path and filled with the same images. And then this code will basically ask for access to your Google Drive and load the images from your drive. But if you haven't downloaded that data set into your Google Drive, it's not going to find anything. You'll get stuck. And so it's specifically this texture, it should be terrain or something. Yeah, terrain data set. So in the root directory of your drive, have a terrain data set folder, and inside the terrain data set folder, you should have all of these JPEG files. Literally, all I did to construct this data set is I went into Google Earth, and it has a save image function. I set that to a big resolution, and I went to interesting looking places and saved an image, and went to the next number and saved an image. It took less than an hour to make this. But of course, I don't have any labels, right? I don't know, or I haven't done the work to say, this is a river, and this is a mountain, and this is farmland, and so on.
Is everyone okay, or does anyone need some help putting this data in your drive?
Yeah.
Okay. It's 180 megabytes. What is it? 114 or something. No, it's not that many, but they're big images.
I think.
Yeah.
Nicholas?
Yeah.
I think the only link that is in the Google Doc is to the actual notebook, not the data.
Is this? Yeah, it says Nicholas data for triplet embedding, and then there's the drive link.
But that is linked to the
Oh, no.
notebook.
Okay. That's not good. All right, let me try this. Yeah, share the link. Just make sure.
Yeah, okay, slightly different.
Yeah, try that one.
Now it's in your I guess it will be
Okay, we'll find out very soon, I suppose. If you put it in another directory, you might just have to change file name in the notebook, so don't worry about it too much. But make sure you do have the data.
Okay, so after we have to Google Maps, what
To make sure that you have that terrain dataset folder on your Google Drive.
Insert.
Can you think of it Chinese? Sorry.
Yeah, unfortunately, this is slightly too big for GitHub, so it becomes much more easy to distribute. Should have put it on Kaggle, actually. Why not, right? Can you post datasets on Kaggle?
You can. You definitely can. So you can upload it, and you can upload your. This is a kernel as well. This is insert.
Oh, nice. Yes. At this point, it probably takes too long to set up.
Oh, you mean now?
Yeah, no, not now, right? In the
Ah,
future. Okay. Shall we? Are we good? Okay. So again, the start of it is loading libraries. Because we're modifying this triplet loss is a little bit non-standard. So there's not like a thing in Keras that you just say do the triplet loss and then you're done, like there was for accuracy and other measures. So we're going to actually have to use a little bit of the actual TensorFlow backend stuff to do this, but it's not it's not too much in the end. Okay, so this is going to be the test. In Colab, you can import, you can get files from your drive. And to do that, you basically use this code. And you can mount the drive, and then you have access to that file system. But what it's going to do is it's going to ask you to go and get an authorization code from your drive, and then paste that into the satellite. And that will give the Python notebook access to your drive under the subdirectory G. Oh, it's still downloading. Right. I probably have to explain something because I was messing with this and I left a fancier version in place. Okay, so now I probably shouldn't actually broadcast this or you'll all get my drive. So just do this. Yeah, especially if this is going on YouTube, right?
Oh yeah.
I mean, your code is regenerated every time, so it should be okay, but...
No, that's not how I work. This gives, actually the code isn't regenerated. I've seen it be reused.
Wow, I'm talking without verifying what I'm saying. This is dangerous.
At least...
I expected it to be regenerated every time.
I know, right? It seems reasonable. close that thing. All right, and then the screen. All right. Then I'm basically going to load in a bunch of different kinds of layers. Most of this I just loaded in so that it's there to experiment with. The actual architecture doesn't necessarily use any of these, but it's something that we can discuss as we actually get into fine variations. The core as before is this conv2d, max pooling, and dense. I need this extra thing activation because I'm going to do a non-standard activation function. So this is defining the model, and at the very end, I have a spherical projection, and it's going to make a three-dimensional space. But what I'm doing with this sphere proj thing is I'm essentially taking the z's and normalizing them. So that means that all of the outputs of this network live on the surface of the sphere. And the reason to do that is that makes it so there's no special central point. Right? 0 could be special otherwise, but if they're on the surface of the sphere, every point is kind of the same as every other point. So it's just another way of calculating it. But honestly, if you didn't do this, it still works. So if you want to delete the last line, this line should be commented out, and this should still work just fine. Or you can use it with it, up to you. And the basic architecture here is it's the same as what you saw before. There's just a few more layers. There's the conv layer, then pooling, convolution, pooling, convolution, pooling, convolution, pooling, convolution, pooling, blah, 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 until the end. Right? It's just more of what you do. The reason for that is, in principle, that would give me access to features that are distributed in a larger receptive field in there. So I think in the network that you did before on the 28 by 28 data, there were 2 convolutional layers. I think one was 3 and one was 5 for the kernel size. So you basically have a 7 pixel window that the classification cares about at any point in space, and then the pooling operation takes all of those 7 pixel windows and summarizes them, finds the strongest activation in each filter from the windows. In this case, we might want more extended features. Like this is higher resolution data than the satellite images that we used before. So before a mountain might have been 4 pixels, but now a mountain might be 50 pixels or 100 pixels or something like that. So we want this receptor field to be bigger. And the way to do that is, since we have a convolution kernel of a certain size, that means that this point is now going to see a neighborhood of that size, let's say. But then if I pool it and do another 3 by 3 neighborhood in this new thing, this 3 by 3 neighborhood is actually a 6 by 6 neighborhood. Or if I pull it twice, it's now a 12 by 12 neighborhood, or a 24 by 24 neighborhood. So as I go down this chain, I see wider and wider and wider areas very quickly. It's not the fastest way to do it. It's not the most quick expansion, but it's generally a good kind of trade-off to have a number of layers that's roughly the logarithm of the size of the thing you want to pick up. Right? So 2 to the power of the number of layers is roughly the size of the percent field you want. Again, no hard rule. So that's the model. And I'm going to use the atom optimizer like before. And then I'm going to load the data. This cell is going to take a long time because I'm loading everything into memory because it just barely fits. So try this and we'll see if your files are on the drive. I'm using 70 images for the training set and the rest for the test set, 44 images. So we can also use the train test split to see whether these embeddings are picking up something that's specific to the data you showed it, or something that generalizes over the distribution of the data. And you can see that gram bar is going up. At this point, is it working for everyone? Are you loading the files and it seems to be loading? Because this is where we find out if you...
It apparently it worked, apparently.
Okay, great. Yeah, well, I would hope that you don't have access to mine. Otherwise, I messed up.
I mean, they do have access to the folder, the shared folder.
Yeah, but not my code, right?
Not your
Okay.
code, but if they delete an image, it will disappear in your drive.
I'm not sure if it's shared with link. I don't know if you can edit it. You shouldn't need to edit it anyway. Just load.
Yeah, but I'm just saying, like, they might.
Okay, well, if you delete the data set, then it's essentially to just stop. But okay, so it loaded. It's using about half of our RAM, but it still fits. And this code here is essentially getting batches. And what I mean by batches is those 3 images, the 2 similar and the 1 different. I have 2 versions here, one that asks for what I consider to be a hard batch, and another one I consider an easy batch, but they're just slightly different ways of getting it. The basic idea here is I'm going to pick 2 images, and 2 of the patches are going to come from one of the images, and one of the patches will come from a different image, just from random locations. And every time I do this, I just pick another 2 from one and 1 from the other. In the hard batch, I put some constraints on how far apart or how close together they should be. But otherwise, it's basically the same code. And then I'm going to assemble a bunch of these into a NumPy array that I'm going to pass into the learning group. So it's a bit of a different way of constructing the data from the generator. Probably the generator way is more elegant. This is just lazy. Okay, so now this is my training loop. It's no longer quite so simple because we have to do this thing here. So what I'm doing is I define a batch size and I'm going to accumulate errors. And when I go through, every time I do a pass of this, I'm going to generate 30 batches and update the weights based on those 30 batches. In order to get the gradients with this custom loss function, I'm using this gradient tape thing that TensorFlow has. If you use PyTorch, it automatically keeps track of derivatives as you do operations. But this essentially tells TensorFlow, hey, start keeping track of the math. And so every time I do an operation inside that gradient tape clause, it's going to tell me how to take the derivative across that thing when I finally want to do the backformation step. And I can just use the model as a function. So I can take the model and apply it to the first member of my, or the first subset of images in my batch. That's the x1s. And the x2s are the ones that are similar to the x1s. I get another one, it's p2. And then finally the x3s are the ones that are different from both, and I get a p3. I then calculate the distances. And I have a couple fudge factors just to prevent numerical instability. If you take the derivative of the square root where the argument is 0, that derivative goes to infinity. So just adding a very small number there can stabilize the algorithm. And then this line here is just that triplet loss term, right? I take the mean of the maximum of either 0 or the difference of the distances plus this alpha factor, this gap that I want to care about. I get the gradients from the tape that I just constructed, the gradients of the weights with respect to this loss. And then I apply the optimizer. And this is basically, this unrolls a little bit of what was really simple in using Keras natively. But this is, since we're using this loss function that involves comparing 3 points to each other rather than 2, you have to kind of unroll Keras a little bit to get this. And then I'm just going to do the same kind of thing for the test to evaluate the quality of the embedding. And then the rest is plotting code that just shows you in real time as you train it what's happening. So I'm going to run this. Maybe, shoot. Oh, okay, this is GPU runtime. If it's very, very slow, yeah, okay, that actually good. It's very, very slow. Check if you are using the GPU runtime or the CPU runtime, because it will be much slower on CPU. So this is just 2 of the dimensions of the sphere, and the third one pops out. And the 3 colors are just the 3 matches. It won't necessarily mean very much if you see a cluster by color. And this is that triplet loss, and this, at least as long as that's going down, it's learning something new that applies to the test set. So we run that for a while and see what we get. Now, so like if we were doing TSE, we would be done by now. So this is heavy compared to just doing map for TSE. But it does scale to much larger data sets than TSE. So with TSE, if I do 50,000 points, it will take a minute or 2. But if I do 5 million points, I guess I'll be waiting forever. And this is just sort of the scale more or less linearly. So it might get a bit better. This is a lot noisier than the just training a classifier. Part of that is because the output is a very low dimensional space, so when things move past each other, they kind of push up the loss. If you were doing this in 20 dimensions or 30 dimensions, you might not see quite as much jagginess in the training. We can see what we have already with this. And then this code is just going to plot an image at every point in the space where that image is being embedded. So you can kind of see visually what this is doing.
How does the margin parameter affect the training time?
How does the output or the alpha?
Margin.
I don't know if alpha really changes the training time so much, but it changes this how severely you want it.
Convergence.
Yeah. I would say it's more about specifying the kind of structure you want the embedding to have. If you make alpha very, very big, what that's saying is that, especially if you use a spherical embedding like this that has a characteristic distance scale, you're saying that you want the global structure to matter, and you'll sacrifice the local structure, right? So every point is going to be pinned by more other points that are trying to avoid or trying to adhere. Alpha is very big. If alpha is very, very small, you're really emphasizing the local structure and sacrificing the global structure, because it's possible for a clump to just be a little bit away and considered independent. So I don't know if that really is going to have such a huge effect on the convergence time. So there probably is some effect, but it's not something I would clear.
Is anyone having a range error? Or
Range
just
error.
Okay, you too. Okay, everyone is having range errors.
That's strange.
It's not too much.
Oh, that's because the list of files is empty, because the directory seems to be empty. I would guess. We go up there to the ramps, because the ones having on a solution. No, it's a constant. Yeah, there's seriously looking. Yeah, you don't have all the images. I don't know. I'll leave it on the video. picture this. Oh, it's the same error. The length of file seems to be 0. Looking for the terrain dataset folder. Oh, it's not there. Scroll up and see. Yeah, because your RAM is not used, so that means it didn't go somewhere. So if you go down to after there to where the image loading, it's after this cell. After this, the next cell down. So you ran that. I guess it basically says, okay, nothing's happening here. You do. Parentheses isn't just. Yeah, so it's not finding this directory. That's the problem. So I think we need to somehow put data into that directory.
Just now.
But it has to be in the same path. So if you should have a folder in your drive called terrain dataset, or wherever you. Yeah, so there's no such folder. So if you can create that folder and then, right? I don't know. Maybe it's better to just do it to the share. Can you? Yeah, because I don't actually see it there either. Can you go to the Google Doc that Bob posted? It's that. And then, yeah, and then click that. And then can you, is there a way to like get this onto your drawing? But maybe it's a different account than you like. Because this one isn't. Okay, that's probably fine.
What did you find?
Maybe. Okay. It's not loading, it didn't see the directory, and the directory is not visible inside the G Drive subdirectory because I think there's like the ELSI cloud account and there's also the personal Gmail account. It was logged into.
So everyone should check that they are in the right.
Yeah, just make sure that the folder exists when you actually visualize, when you look at the file system inside co-op.
It exists there and they're the same.
So the notebook and the data set have to be in the same directory. If they're not, you can just access it from another directory.
Well, the directory in Google Drive has to have the same name unless you don't, because it's explicit. There's an explicit path in the code.
Change the path.
Right, but like in this case, the directory doesn't even exist on the drive. So like,
And here it exists and it has the right path and it's not found. I mean, it doesn't say not found, but it says a length file
that there are no
low or
files.
something.
Or maybe just save it on your local machine and change the path to your local.
Can you access your local machine in co-op?
No,
No?
No,
no, you
I
can't.
don't think so.
Oh, really?
Yeah, you have to put all your data on Google Drive.
Yeah, or I mean, inside Colab.
Well, actually you can, but it's a little bit side. I just remember you have to upload the file.
Yeah, you can't. You have to upload it. You can't access. Trying to think. because my collaborator managed to access my files that I shared on Drive. Not for this, but for a different thing. So it's possible.
I think it should be possible.
And then at the end, like check the encoders file and make sure that
No. I mean, okay, maybe we can try, but I think it would take time.
Just because of the
This one? And this didn't work.
no, because this is my another Gmail account.
Can't you just access it from here? From your own correct email account?
correct Gmail. Is there any reason why someone would have a lot of RAM used by default in Colab before they run code? Is there any reason why someone would have a lot of RAM used in Colab before they run code? Because like even without the files loaded, it seems like half of the RAM on this Colab was used, and it's preventing the dataset from actually fitting. Could it be because of a different runtime?
Maybe clear.
Just go to runtime. Okay, yeah. Maybe if you saw memory problems, if you go to runtime and you set all runtimes, because maybe this morning you can set this is so easy. Whenever it works. So it's just like even there it's still only about half the use of the processing. But at least it's your passion is that it's all processing.
No, it's
It's almost certainly not what it's almost. Yeah, is it?
You didn't think to.
It's always
Because which one is this? Because it's the one that we got. So I will put this and I will also attach this with some extras. And this is the one that we got here. Okay. Let's use this. So you have to put some of it.
passion. Yeah, try to set all runtime. Where it's from. And then set all runtime.
So, again, I should use the same.
Yes. Yeah, now try to run
Did you find what was wrong?
Well, now the issue was RAM, and I think it was some other collab runtime that was eating up half the RAM.
Yeah, I also got all of them close here.
Yeah, so if you're running out of RAM, reset all runtimes and run it. Runs really well.
Because
Okay.
I haven't run.
So anyway, I guess you can kind of see it's picked up some really obvious things, like very light colored images on one side and very images on the other side and high texture ones and things like that. You'll see a lot of that kind of thing in doing these triplet embeddings, especially low dimension. If you have more data, you train it longer and things like that, you might also see more subtle structure getting picked out. But even this is going to be kind of interesting if we look at it on specific examples. So the way that we did this network architecture, there's a bit of a trick here. Where did it go? It's up here somewhere. Notice I don't have a dense layer anywhere. So my output is actually still a convolutional layer. And that means if I make the input image bigger, it doesn't really matter to the network. Everything's defined as a local operation. So if I make a bigger image, it's just doing more of those local operations. My output won't be a point of the image, but an image in these new RGB coordinates based on this embedding space. So I can take a big image rather than these little 64 by 64 patches. Here, this IDX thing is just going to say which image from the test set do you want to look at. There are 40 something of them, so you can pick one. 22, let's say, I don't know what that one looks like. And what it's going to do is it's going to run that image through the model, and then it's going to actually show you spatially what the embedding looks like as a function of each coordinate. And you can see that, I don't know if this one is as good as the previous one, but it's picking up the mountainous terrain and this kind of region here. Depending on how you do it, it may or may not end up getting tricked by these. So the Google Earth data has a lot of patches that are fused together to make the collected image, and sometimes they don't normalize all the patches in exactly the same way. So you see a lot of these boundaries here, like this diamond-shaped feature and things like that. Depending on how I did the embedding, I might get an embedding that picks up on that, or I might get an embedding that actually avoids to ignore that. And that's a subtle point. So if, for example, I really, really cared about locality on the pixel level, so I say, like, I want to do the triplet embedding with all three patches taken from one image, but the third patch is a faraway patch and the other two are close, right? That's something I could have done just as well. In that case, it's going to say, okay, anything that varies over an image is worthy of kind of being embedded differently. So if I have one region of one color in an image and another region of another color, I'm going to learn an embedding that's sensitive to that. But here, because my sense of similarity is the same image or different image, it becomes kind of invariant to things that can vary within an image, but sensitive to things that vary systematically between them. And these kind of color patches are common enough that it essentially has to learn to suppress that feature because it's not informative about whether you're in the same or different image. So doing it this way, it kind of encourages it to focus on the things that are more about global terrain features. And I guess basically with the rest of the time, like I would just playing with it and try some variations. You can make small changes to the architecture, use a different activation function, retrain it, or even use a different way of selecting the similarity criterion, although then you have to rewrite that from code. And you kind of see what sorts of things to do. I don't have like it's not a sudden here's where you're done because this is an exploratory analysis. I guess this one. What's that? Oh, okay, that's a bit obvious.
Really? Mm-hmm. I thought maybe when you put it in the wrong directory, it would work.
Yeah, it's
Okay. Yeah, I know. I finished too early. I guess triplet embeddings didn't actually take as much time as we thought.
you finished
Oh,
just
you're
on time.
perfectly on time, right?
Yeah.
4:30.
Yeah.
Yeah.
Oh, okay.
Sorry to disappoint you.
Yeah. Any questions or just things? Yeah.
So, for example, you said Google Images has no straight line, right?
Yeah.
Based on the weighting that they're for.
Yeah.
And so, if we wanted to have some kind of neural network that knows those lines, what would we do? Should we increase the number of layers, or should we?
Well, so like if you in this case, I had two different ways I could have constructed the similarity, right? I could have said, and I don't want this to be like an authoritative answer, but this is what I ended up doing when I saw that this happened, right? So there are other ways we could approach it. So what I started with is I said, okay, I want like, I believe, or my thought about this image is that maybe it has, mountains and forests and a river through it. and that there's a correlation function which is much smaller than the scale of the image that determines similarity. So what I really want to do is I want to take like two images like that and one image like that as the pivot, or as the hard example, the negative example rather. So these are similar and different. And I just constrained it so this is like less than 64 pixels away, and this is greater than 256 pixels away. So when I did that, I found that the triplet embedding almost entirely picked up on those edges because edges is the only thing, or the strongest feature. Because, of course, you have these patches whose size is around the length scale that I chose as the threshold between similar and different. If I had chosen this to be, say, 8 pixels and 64 pixels, I would probably suppress that feature a bit more because I would be, similarity and difference would not actually matter so much on the length scale of the feature appeared, but I would still actually probably see it. But I went the other way, and I said, okay, the entire image is going to be considered to be similar, even if it has different terrain. Right? And in that case, that ends up suppressing that detail because knowing the normalization of the satellite over that patch, it's only really meaningful relative to other patches. Like you wouldn't be able to look at one Google Earth photo and say, the normalization is really screwed up on this photo. You'd only be able to see if it changes abruptly. So by using the entire image as the similarity definition, that means that these things that only matter locally, but they don't differentiate between whether I'm in image A or image B, they get ignored by the network. And the network will just automatically learn to suppress them because they're not informative features of the question that I'm asking them. So if you can do that, if you can ask a question that's sensitive to the things you care about and not sensitive to the ones you aren't, then you don't. That is a good way of going about it. But that also, maybe that wouldn't have worked, right? But maybe if I had done that, it didn't work, and then I would have to think. And I would have to basically say, how can I pin down this feature that is being detected as varying, but is spurious? Is there some way that I can actually hold something constant, such that I factorize the data between the variation that's spurious and the variation that's not? And then I would have to think a lot about what exactly I'm doing, and I'd have to think a lot about what exactly characterizes the way in which this feature appears in the distribution of the data. And I might be able to construct a more complicated network that would actually forcibly remove it. So for example, let's say I hand labeled a couple examples where there was a gap like that. I could train a network to basically predict whether an image has a gap. And then I could try to make it so that that network fails to predict whether there's a gap when it looks at the embedding. So that would force the embedding to not contain information that's predictive of whether there's a gap. But that starts to get more elaborate. And that's the kind of thing that we can do. Like as you get comfortable with the flexibility of neural networks, you can start to devise these ways of building a secondary neural network to subtract information out from the first one, things like that.
Okay. So
But it's a bit complicated for today.
Okay, so it's not as simple as 21 hyperparameter. It's not as simple as 91 exponential.
No.
It's much more.
Yeah, there's a whole bunch of tools you can use, and then you're kind of making choices of what order to try the tools in. I mean, the general idea of how to subtract information from a neural network is a useful one, so maybe it's worth going over. It's a little bit, I kind of didn't want to cover because this is already going very far in a very short time. But the basic idea, this is kind of what underlies what's called a GAN, or a generative adversarial network. So that you have something, let's say you have a network that makes an output Z from X. And then you really don't want Z to contain information about some other label Y, right? So you have another network here, call this the discriminator, call this the generator. The discriminator takes in Z and predicts Y. And then you notice all I've done is I've stuck two networks together, but I can train this as if it were one big neural network. Except that I have to do two loops. I have to make this thing as good as possible. So try to maximize accuracy of Y or minimize log loss. And then this thing here has to minimize accuracy of D. And also do whatever ancillary task that I actually want Z for, like the triplet embedding, or if I want to decide whether to use someone alone. Like maybe I want to have an algorithm that predicts whether to use someone alone, but I don't want that algorithm to take into account something like race or gender. I could have it make an embedding that's going to be used to make the final classification of do I give them alone or not. Have the secondary thing try to figure out the race or gender from that embedding, and then try to make it so this fails, right? So I can actually force it to not pay attention to that information by having this kind of min-max game. So that's a useful kind of general architectural trick that you can use. Maybe if, I don't know, people are still interested in this stuff after today, we can do like weekly sort of go over a paper or have something like that, like a journal club, and look at some of these special cases or some of these techniques that people are working on. But this, yeah, probably this goes a bit far for introductory. Should have just given the talk on GANs. You can use this to make photorealistic images. This is how how some of the fake stuff works. You say, I don't want to be able to know if it's real or fake, and then you make it so it's forced to use a representation of images that it can't be told whether it's real or fake. Well, GANs are not so heavy compared to other things. It's not reinforcement learning.
Oh, but to get really, really high resolution photorealistic images, you need to train.
It's about a month on high-end GPU.
That's
would
a
say
lot,
for
right?
the best
I would consider that a lot.
It's still within the, I've done one, right? Like it's within the range of an individual researcher. It's not like you have to be Google to do it. That's what I'm saying. We did a butterfly GAN, progressive GAN. It took 2 months to train.
Really?
Yeah.
Who paid for the compute?
It's just my computer sitting in ELSI
Oh, you're training it on one GPU?
Yeah, one GPU
from
for 2 months.
Sir.
Yeah, it's just at the threshold of what you can do. If you're willing to spend
What
2
is
months
the
on a computer.
lifetime?
Let me see if I have one. I don't know if I have one.
Yeah, if you train that in
Oh, yeah,
the
this can go on YouTube.
Oh,
Oh wait, I'm going to stop the
okay, then maybe.
wait.